Hello there, welcome back to our channel. And as you can see on your screen, we have this common emitter amplifier, and this is a single stage amplifier where we have biased this transistor Q1, which is a part number 2 and 2222. It has a beta factor of 200 that we can see by right clicking over it and clicking here, seeing the spice model where we see the beta factor is 200. And we have done the DC analysis where we see the operating points of the circuit, whether the transistor is properly biased or not. We have seen that in our previous models. Now this time we are going to build a multi-stage amplifier, and multi-stage amplifier suggests us that we'll have a two stages. So this is the stage number one, and the output of this stage will be fed as an input to the second stage that we will construct in a while now. Before that, we would like to show you the transient performance or time domain simulation of this circuit. So what you see, we have this transistor Q1, the collector resistance is RC, the resistance in the emitter is right here, which is 220 ohm. These values of these resistors have been chosen in such a way that the transistor is biased in an active region. From the load line analysis, we see that the transistor is biased in the active mode. The capacitances in the input side and the output side, they are called as coupling capacitances, and their values are chosen in such a way that the reactances are minimal at the desired frequency of interest, which is the signal frequency that we want to amplify a signal of. And these are called coupling capacitors, so their reactances will be minimum at that frequency of operation. This is the bypass capacitance, and this is going to be short at the high frequency signal so that this emitter is connected to the ground. And here I have applied the sinusoidal signal now with the amplitude of, let's say, 100 millivolt. Let me right click here on the voltage source. So this is 100 millivolt signal with a frequency of 1 kilohertz. And that's it. And I'm going to run the transient analysis. As you can see, this is the dot trans. I am using the 12 volt DC power supply. So let us run the simulation first. So if I click run here, I see that this is the VB. It is the voltage at this node, which is the voltage at the base of the transistor. But I want to plot the V2, which is my applied signal. So if I click here, that is the signal in the red. So I will just delete this trace, and I will zoom this signal. So as you can see now, I'm applying 100 millivolt peak signal in the red form, and the bias level of that signal is about 0 volt, of course, and it goes to 100 millivolt, then it goes to minus 100. So 200 millivolt peak to peak. In response to that, this is an inverted output. It is at the node VO that I see here. So this VO is here. So I will just get them on the same. I have plotted them double. So I will just zoom in now and look at the DC level of this signal is also starting from 0. So, and it goes to about 500 millivolt peak. So you have a gain of about 5 times, which is set by the resistor ratio of RC and RE. So RC is about 1200 and RE is about 220. So the about 5 point something is the gain. The RC divided by RE is your gain of the circuit. So this is our amplifier, common emitter mode, and the beauty of this circuit is that the input impedance of this circuit is relatively high as compared to common base or common collector configuration, and the output impedance of this circuit is moderately low. So we would like to have an amplifier in some applications where the input impedance should be infinite or very high, and the output impedance should be very low or in ideally zero. So to have that uh, situation, we would like to cascade two stages of the amplifiers. And the solution to that is we would now add one more stage, which is the common collector in front, followed by this amplifier. So let me show you that. So what I'm going to do here, I will just press F6. That will make the duplicate of this transistor. So let me just put that there. Just a second. Okay, just a minute. Yeah, right here. I will press F6 for example. Okay, it doesn't really make sense. So I will do one thing. I will just click File, Edit, and then here duplicate, and then I will click on transistor. I will have this transistor right here. Then I will also have register RE, and that is another register here. Then I will need a ground, that I will do it here. Then I press space bar from the keypad. Then I will click the wire here, which is F3. Then I'm going to cascade two stages. The first stage is common emitter, and the second stage is gonna be common collector transistor. So let me just make the wire connections like here. Now the output of the first stage becomes an input to the second stage. And this is how it goes. And then I need final output or the output of the second stage. I will then right click this net. I will click label net. I will say this is my final output V out, and I will choose the output port. Then I will click OK. I place it here, and that's it. I made the connection. Then I press escape button from the keyboard. Then this symbol disappears. Now I don't need this capacitor because I am connecting directly the output of the first stage to the input of the second stage. So what I will do is use the scissor and cut this capacitor right here, and then click wire and make the connections back to the two ports. So output of the first stage is VO, output of the second stage is V out. The transistors are chosen to be same. Now, what about the value of RE? So yes, I would like to have it, let's say 500 ohm, and we'll see. Now, what is the role of this part of the circuit? So you see now, the this is a common collector uh, circuit where the input is applied to the base and output is taken from the emitter for this NPN transistor. So the input side of this circuit is again the base and the collector, and the output side of the circuit is the emitter and the collector. So the collector is common if you see the AC small signal model of this circuit. And the output of this circuit would be the voltage at the base minus this PN junction drop, which is the forward bias voltage of this transistor. So if you have like, you can say 1 volt DC bias level minus 0.6, which is the forward voltage drop, will be the output 0.4 level will be the DC bias level. And from that DC bias level, you will have the swings, AC swings of the output signal. So now we are done with that. And the advantage of this common collector circuit is that it acts as a voltage buffer. So what it has a very high input impedance, and it has a very low output impedance. So it is it this stage common collector can be inserted for impedance matching. For example, let's say you have the output impedance of the first stage, which is a common emitter, which is a not very low, so it cannot drive the loads of any values. If the load requires high current, then common emitter stage, the first stage, may not be enough to do that. So what you do before driving the final load, you place this stage in between the CE and the load so that it matches the very low output impedance of the load side and the very high output impedance of the source side, which is the common emitter here. Okay, so the output of the common emitter can drive the base of this transistor because it has a very high output impedance, and the output of the common collector will be able to drive a load demanding any magnitude of current because of its purely very small output impedance, which is in the case of, let's say, RE, set by RE. Now, having done that, the voltage gain offered by this second stage would be less than 1 or approximately 1, because we've seen that the output will be the voltage at the base minus the forward voltage drop of these transistors. Okay, and now we have plotted VO. Now it's time to plot V out, so we'll do that. So we'll run the simulation again, and on the same plot I would like to click V out and look at the green one, and the value has been decreased. The difference between the two levels is the output level is about, we can see that is about 6.5 in the blue, and this one is about 5.8. So obviously 0.7 voltage drop. This is the forward voltage drop, what we just said. Okay, so zoom to fit. What about your swings? So as you can see that again, it does, this stage, second stage, doesn't offer any phase inversion, so output is again the inverted. For the positive half cycles, you have negative half cycles in both the stages, VO or VO out, and for the negative you have opposite signs, and then the gain would remain the same. So now look at the DC bias level. The DC bias level has been changed because you have removed the capacitance from here. Now the input signal starts from 1.08 to 1.16. So it is again 100 millivolt level. And then you have the output DC level is about 6.2, and then it goes to about 5.6, something like that, so 600 millivolt. So again, output is 5 times larger than the input, but the DC bias level has been changed there. So this is how you can design the cascading or multi-stage amplifier. What about we want to simulate the AC response of the circuit? So what we'll do, I just use the scissor, and if I cut it right here, and then if I run the simulation again, so obviously green disappears, but look at this, let me delete this trace and zoom to fit, and look at this signal, input output signal. I have this like one. So 6.2 level is the DC bias level because I have removed the capacitance here. So I need to place that capacitance here because the output is AC coupled to the load. Now, let's place the capacitor also. Maybe we'll just put the scissor here, and we'll say that we'll press F6. That is your capacitance here of the 10 microfarad. Then you click the wire, and you just connect them together. in the fashion, and then click simulation again. Now, oh, you don't really have oh, you need to disconnect this wire also, because you have now connected this one. You need to separate those stages. Let's do that. Now look at this. The DC bias level for the input 6.2, and then you have a swing, but the DC bias level of the output is now 0. And from the 0, you have about 600 millivolt signals. So this is the importance of adding the capacitance there. Okay. If you directly connect if you AC coupled this output to the input of this stage, you can also investigate the effect of it. So what you do is connect signal, the output signal, then have a power supply to the second stage and run the simulation and look at that. This is how you can do that. You have like a 0 volt DC bias level, then 100 millivolt, and the output here is about 300 millivolt, and it goes to minus 200. So it's about, how much is the, or from 300 DC level you have like 800, so gain is 5 times. So it makes sense, right? And what about this VO output? But the VO output got clipped, so you don't have really any amplification. So the solution is to remove this capacitance, because you can't really have that there, and directly couple the uh, signal right here, because you have the forward voltage junction drop, and PN junction capacitance becomes the load capacitance to the first stage. Click the run, and now look, you have signal back to your original level. Okay, that's it.
After this, it's time to run the AC analysis of the complete multi-stage amplifier, where we would try to obtain the Bode plot for these combined circuit. And as evident from the time domain simulation, we don't have any gain enhancement due to adding of this second stage right here. Rather, we would just have the second stage for the impedance matching. The whole purpose of this multi-stage amplifier is that only. So what we need to do is right click this voltage source there, and select the AC amplitude to be 1. We click none here, and we click OK. And after that, we need to run the transient. We need to disable the transient analysis and enable the AC analysis. So look what I'm doing here. I will just remove that sign and put a dot here in front of AC analysis. With that said, I will run my simulation so I can show you. I will click run, and well, let me clean those graphs here. I am only interested in the output. That is what the first stage output and the second stage output. Now look at the response I am getting here. It's a kind of the gain for the VO. The blue one is the output at the stage 1, and you see that I have a constant gain of about 10 dB for the frequency range from DC to about 10 kilohertz, and then I have a kind of band pass response. Here is little bit flat in the mid frequency range, and here also the same. And the dotted lines are the phase, which is given on the y-axis, the phase variations. But this is about in which signal frequency you want to amplify, and what is your gain requirement. Based on that, you can tune your circuit right there. And if you kind of remove this second stage and want to just evaluate, just let me take the scissor click cut here. Oh, okay, just a second. I have to use the scissor here, maybe. Uh, right here. Let me do that. Cut here, cut here also, and then rerun the simulations. And if you see now, the blue one is the kind of same graph. We don't have any change here. So we'll do the undo, that is F9, and we'll run the simulation again to get our plot of V out and V in. We'll delete this trace. Now, yeah, so you got to see that what is your gain and what is your signal frequency. Use like 10 dB because your signal is about 1 kilohertz. In the time domain we had this, so gain was about 5 times. So 20 log of 5 would be your magnitude, right? So it's like about 10 dB. That makes sense. And the phase at that frequency is about the minus 180, which is the phase inverted. Look at this blue line, dotted one, and on that level, you see the phase right here is about minus 180. Or just zoom in this portion and look at the phase at the frequency of interest is about 180 degree, right? Again, right click and zoom to fit, and you will get that. So we got the response of these AC analysis of the multi-stage amplifier and the DC analysis we have done earlier. If you are still interested in doing the DC analysis just to verify the currents and the voltages in the circuit, especially the collector current, base currents of both the transistors and the bias voltages, you can have a look at our previous modules. So hope you got the feeling about how to make multi-stage amplifier, what it is, how it is used, and the main advantage is for this particular category is about impedance matching. So common collector is that you can have a common emitter at the second stage also. So it depends. You can have a common base also. Depends on your requirement. Okay. So if you like this video, click the like button, put some comments based on what you feel, what you think, and let us know your preferences about what you would like to learn more. Share it with others for wider reach, and till then, stay tuned for more engaging contents like this and some other topics. Wish you happy learning.